Good evening, everyone, and very warm welcome to you on this, actually up in the north of Scotland where I am. It's a beautiful evening here. We're still up about between 6 and 7 degrees, so it's really nice out. Thank you for all attending tonight. That's very good. Just a way of introduction before we get started, my name is Gary Johnson. I'm chair of the Scottish Centre and be your host tonight. And we have two of our student delegates to give us wonderful talks tonight. And before I introduce them, I would just quickly like to encourage you all to have a look at the RMetS website. You'll see the screen up there just now, or go to www.rmets.org, and it's a great organization. It's free to join, so please come along. There's a lot of benefits from being a member. Just on the talk tonight, the quality of sound and picture should be good. We are using Zoom as a medium, and hopefully you will be able to hear and see us okay. These talks are being recorded and will appear online just shortly after the talk tonight. We do need permission from both speakers before it can be released, but that will no doubt come through. So hopefully the next 2 or 3 days you will be able to watch this again online, or tell your friends who will be able to listen to what Dan and Ned have to say. Once we start the talk, you will see at the bottom there's a bubble for putting any questions or answers, any questions into. And what we're going to do is have both our speakers tonight speak, and we'll allocate time afterwards that for answering questions jointly between the two of them. So if you can direct your questions to whoever you would like to answer, it would be really good. If you notice something on either of the talks, on any of the slides you want to refer to, please note either the title or the number of the slide, so we can go back to that slide if you wish to refer to it. So in saying that, we will move on, and I'm very pleased tonight to welcome you to the Royal Meteorological Society Scottish Centre Postgraduate Showcase. And tonight we have two students who are going to talk, and the first one to talk tonight is Mr. Daniel Skinner, Dan, from the University of East Anglia, who is going to talk about the decalled variability of the extratropical response to the Madden-Julian Oscillation. So, Dan, over to you.
Thank you very much, Gary. I'm just going to share my screen so that you can see the slides. Okay. Can you see that the slides?
Yeah, they are good. Yeah.
Perfect. Okay, so hi everyone. Thank you all for coming. It's great to be here to talk to you all. As Gary said, I'm going to talk today about decadal variability in the extratropical response to the Madden-Julian Oscillation. So, just going to give a bit of an outline of the talk today. So first up, I'm going to actually introduce what the Madden-Julian Oscillation is, in case some of you aren't familiar with it, and also a little bit of an outline of teleconnection patterns, what they are, and kind of what we mean by that term. Next, I'm going to talk about the kind of question we're trying to answer in the research I'm presenting, and how we go about answering it. I'm going to show some results, so the changes in MJO teleconnection patterns over the last 50 years, and then also talk a little bit about how those changes are actually going to impact us. So why does this matter, basically? So that's kind of roughly how the talk's going to go. So we'll start off with what is the Madden-Julian Oscillation, or the MJO. So the MJO is the largest mode of subseasonal variability in the tropics. So what that means is we're talking kind of timescales of less than kind of a season or a year, but more than kind of a week or so. And we're looking in particular at the tropical atmosphere. So in particular around the maritime continent, so kind of Indonesia kind of area. It's characterized as an area of enhanced convection, which moves. It starts in the Indian Ocean. It moves eastward across Indonesia and then into the Western Pacific Ocean. So we'll see that in just a second. As I said, the Madden-Julian Oscillation has a period of about 30 to 60 days. It's quite a broad range. This isn't so. Although we call it an oscillation, it's not very regular. Its period can range from about 1 to 2 months, but it sits somewhere within that range. And the reason we're interested in the Madden-Julian Oscillation here in the UK is that it acts as a source of predictability for the extratropics. So what that means is if we know what the Madden-Julian Oscillation is doing, that can help us to predict what the weather is going to be like in the extratropics, which is great for our weather forecasters. Okay, so that's the MJO. Here is just a little picture, so hopefully you can kind of visualize this a little bit better. So as I said, we've got this area of enhanced convection, so this upward motion. That convection then leads to kind of wetter, stormier weather. And this is kind of coupled up with an area of decreased convection, so this downward motion, kind of sunnier and drier weather. And this kind of package all moves eastward across the from the Indian Ocean, across Indonesia, and into the Western Pacific. So, now we know what the Madden-Julian Oscillation is, how are we going to go about measuring it? How are we actually going to describe this thing? So we use something called the RMM index. It was created in 2004 by Matt Wheeler and Harry Hendon. And it's an index we use to basically describe where the MJO is by way of the phase and how strong it is at any point in time by the amplitude. So the phase we give as a number between 1 and 8, with phase 1 meaning that the enhanced convection is over the Indian Ocean, and phase 8 kind of looping back around so that the convection is in the far West Pacific and then starting again in the Indian Ocean. The amplitude, we normalize this number. So an amplitude of 1 is kind of your average MJO, and then anything greater than 1 is particularly strong. Anything less than 1 is kind of weak or inactive. So what do these phases look like? Just to give you an idea of kind of physically where the convection is when we're talking about these phases. So here we have a little animation which shows the OLR, the outgoing long wave radiation, which kind of acts as a analog for convection in the blue and turquoisey and brown colors. So blue, turquoisey blue is increased convection. The brown is decreased convection. And you can see in the earlier phases, we have this increased convection over the Indian Ocean, moving across the maritime continent and then into the Pacific from in the later phases. So that's kind of a visual representation of what we're talking about, what we mean when we talk about the different phases of the MJO. It's just where these centers of convection are. So, as I mentioned, the MJO can affect the weather in the extratropics, and that's the topic of my research, these so-called teleconnection patterns. So when we have this enhanced convection in the associated with the MJO, we have this upward movement of air, and that air has to go somewhere. And what that means is that we get divergence in the upper troposphere. You get this upward movement of air, which then has to move outwards, and that outwards motion will move meridionally and also zonally. So you're going to get this kind of divergence in all directions, including kind of north and south up into the extratropics. Now, when this divergence causes a poleward shift in air, that is then going to interact with the jet stream in the mid latitudes. And when you get this, so the jet stream is moving west to east. You've got this divergence, which is heading towards the poles. And because they're at right angles to each other, you're going to create vorticity. So you basically get spinning in the atmosphere. This spinning, this signal then heads into the extratropics and travels around the world as a Rossby wave or a planetary wave. These are huge scale waves which move through the atmosphere, and in the extratropics, these waves will interact with other weather systems and will alter the general kind of circulation and weather patterns in the extratropics. So how are we going to kind of visualize these patterns, these changes in the atmosphere? So the way we're going to do that is we're going to look at some lagged composites. So a lagged composite just means that we are, so we take all of the days in which the MJO is in a given phase. We then step forward by however many days. In this case, we're going to be looking at a 10-day lag, because that's about how long it takes for this signal to go from the tropics, from the MJO in the tropics, over to the extratropics, kind of around the Atlantic kind of area. And we're going to then average over all of those days, which are 10 days after the MJO phase that we've been that we're looking at. So you can kind of think of it as the average change in the atmosphere 10 days after the MJO has been in this particular state. We're going to look at upper tropospheric stream function. So this is a really nice way of representing the winds. Rather than having to think about a kind of left and right and then up and down, you have one single value. The thing to remember is just that the winds will follow contours of stream function. So I'm going to show this as a contour plot. The winds will follow the contours, and around the positive values, so the solid lines, we're going to be moving clockwise, and around the dashed negative values, we're moving anti-clockwise. So I'm just going to show an example just so you can kind of get your eye in a sense. So this is a 10-day lagged stream function after phase MJO phase 6 between 1974 and 2018. So you can see we've got these different centers of circulation. You can see this cyclonic anomaly over Southern Asia. That's what we call the Rossby wave source. So that's where the MJO, so it's actually the suppressed phase of the MJO is interacting with the jet stream, and we get that spinning that I mentioned. But you can see over North America, South America, and over Europe, we then get these kind of domino effects in a sense. So we see these changes in the atmosphere far away from where this disturbance started, and that's kind of what we're interested in, these centers away from the tropics. So that's the MJO and teleconnections, a bit of an overview. Now I'm going to talk a little bit about the research that I've been doing and how I've been looking at these things. So I've mentioned that that there's these teleconnection patterns. We know that there's this predictability based on what the MJO is doing and how that affects the extratropics. what I'm interested in is whether these patterns change on decadal timescales. So if we look from kind of one decade to the next, are these patterns changing? Is that kind of knock-on effect changing? Now, just for context, in the list there is there has been research into variability on shorter timescales. So we know that the El Nino Southern Oscillation will modulate changes in MJO teleconnections. And I'm not going to say too much about that because Ned's going to be talking about El Nino shortly. But what I'm interested in is these longer timescales, because that's not something that we really know too much about. Second question is, if there is these, if it is changing on decadal timescales, how is it changing? Why is it changing? Are these teleconnections being modulated by other modes of variability? So we've got a couple of modes: the Atlantic multi-decadal variability or the Pacific decadal oscillation. They're two kind of really key modes in the climate system on these long timescales. So could they be causing changes in the teleconnection patterns? The third question, and this is kind of specific to the work that I'm presenting today, is can we find evidence in reanalysis data to start answering these questions? So we can look at models, but can we actually look at observational data, or in this case reanalysis data, to find evidence of decadal variability? That's kind of key to what we're looking at today. And then the fourth question that we're asking is, can we also use climate models alongside that to provide greater insights? And that's something I'll touch on a little bit at the end. So how are we actually going to try to answer these questions? So the setup for what we're doing. So the RMM index, this index that I mentioned with phase and amplitude, which describes the MJO, because we need outgoing long-wave radiation data from satellites to be able to define this index, we actually have index values from 1974 up to the present day, which sounds like quite a long time, but is, when we're talking about things that are varying decade to decade, is really not that long. I've just added a little note here that we don't have any data for 1978 because the satellite went down. So there is a bit of a gap there, but pretty much 1974 to present. And that's the time domain that we're going to be looking at today. As I said, we're looking for evidence of decadal variability, and we're hypothesizing that these two modes, the AMV and the PDO, are potentially going to be modulating this variability. So if we're going to find evidence of decadal variability, we think that's where we want to start looking. I'm only going to be talking about winter, boreal winter, so Northern Hemisphere winter. So that's November through to April. Just because that's when the MJO itself is most active and when its teleconnections are most active. Again, if we're going to find evidence of this variability, it's going to be in winter. So from here on out, we're just going to be talking winter. And the way we're going to compare, kind of look at this decadal variability, is it's nice and simple. We're just going to split our time domain into two non-overlapping segments. So the problem with only having a relatively short time domain is that everything that we're talking about is we're looking at long time averages, kind of climatological timescales. And to look at variability over climatological timescales, you need a lot of data. And so splitting our domain in half is kind of the middle ground where we can still have segments which are long enough to do some meaningful analysis on, but we can actually see whether things have changed. So here's a timeline where I'm showing, so I've shown ENSO completeness, but we've got the PDO and the AMV in red and orange respectively. these are these two low frequency modes that I mentioned. And what we can see is that over our time domain, we actually have two quite nicely set up segments where if we pretty much split down the middle, we can get one segment in which the AMV is negative and the PDO is positive, and then the reverse for the second time period. So this actually is it's complete fluke, but it works massively in our favor, because it means that if we take these two time segments where these two modes are in different phases, we're more likely to see any variability if it exists. So here on out, I'll just refer to period 1 and period 2. Just for reference, period 1 starts in 1974, so November 1974, and goes up to April 1997. Period 2 is November 97 up to April 2018. And of course, we've got this 1978 missing. But by taking these two segments, it means that they're both got the same number of seasons in there. Okay, so what do these two time periods actually look like? Because we've kind of relatively arbitrarily split into these two time periods. Of course, we've chosen those two time periods to maximize the chance of finding decadal variability by picking it based on these two modes. But what do these two time periods actually look like compared to each other? So I've got a couple of plots just to illustrate how the atmosphere and the climate system is different between these two time periods. So first up, I've got a plot of the difference in sea surface temperatures between the two time periods. So this is the second time period minus the first, so it's the change going forward in time. And what we can see is considerable warming in the North Atlantic. That's consistent with a switch from the negative to the positive phase of the AMV. So that's good. That's what we want to see. We see this warming in the central North Pacific, warming in the South Pacific, and cooling in the equatorial Pacific. This kind of 3-bar pattern is the PDO. So that's moving from the positive to the negative phase of the PDO, which again is what we expect to see, which is good. Both of these phases correlate with a cooling in the Southern Ocean. So this kind of cool Southern Ocean is down to the AMV and the PDO being in their respective phases. And the warming in the Indian Ocean is more consistent with a general kind of climate change, global warming trend, which of course, because we're looking at observational data, will be a factor. So that's what sea surface temperatures, which are of course a key driver of the atmosphere, look like. We're going to be talking about the upper atmosphere because that's where these Rossby waves propagate. So here I'm showing something called the stationary Rossby wave number for the two time periods. So period 1 on the top and period 2 on the bottom. I'm not going to go into too much detail about what this number is, but effectively you can think of it as a kind of refractive index in a quite a crude sense. So Rossby waves will tend to refract towards areas of higher local Rossby wave number. So what that means is where you get these kind of strips of darker colors, the Rossby waves will tend to propagate along those lines as a waveguide. And I've marked on 4 kind of key waveguides in each plot, and you can see that 3 of them, so the North Atlantic, South Atlantic, and South Pacific, are pretty much identical. There's very little difference in the structure of these waveguides from period 1 to period 2. But in the North Pacific, we do have quite considerable change. So if you look on the green plot, so the second time period, if you look to about 140 west and about 30 north, you'll see this local minimum in the Rossby wave number. And what that'll do is deflect waves which are traveling down this North Pacific wave path into Canada and so British Columbia in the northern US. Whereas in the first time period, these waves were kind of joining into the North Atlantic waveguide. And we'll see some of the effects of that later on. So basically, we've got changes in the sea surface temperatures, and that means we also have changes in the structure of the upper atmosphere, or the upper troposphere, I should say. So that's kind of our methodology, a bit of climatological context. So let's excuse me, let's actually look at some results. So as I said earlier, we're looking at these 10-day lag composites, so similar to the one that I showed you earlier. And we're going to we look at these composites for each MJO phase and for each of the 2 time periods. What we're looking for is differences between the 2 time periods, and so I've plotted both composites in contours, and then shaded areas where the difference is statistically significant. So the idea of the shading is just to draw your eye to areas in which there's a considerable difference. As I said at the beginning, there are 8 MJO phases. I'm only going to show you 4 of them just because of time and because these are the ones where there's the most interesting results. So if we look at phase 1, so this is when the convection is over the eastern Indian Ocean, so western central Indian Ocean. You see that Rossby wave source over kind of India and Pakistan kind of area. Just want to draw your attention to this. If you look at over Canada, we see this real kind of considerable change in the circulation, where we did have this positive stream function anomaly in the first time period, so the purple time period. We've now got this big negative stream function anomaly in the second time period. And that happens to be exactly where we saw that change in the waveguide. So we can actually see the effect of that change in the waveguide because the circulation response to the MJO has changed over North America. We also get a change in the North Atlantic. This is going to be key to the weather in the UK. It's going to kind of affect things like the North Atlantic Oscillation. So these are a couple of really key differences to focus on. In phase 2, we see something very similar. We again see this big change in the circulation over Canada and Alaska. It's shifted slightly from phase 1. But what we don't see as much is the change over Europe, which is interesting, or over the Atlantic at least. In phase 5, so this is when the convection has moved over the maritime continent and is now into the Pacific. We again see this big change over Canada. Now we have a positive stream function anomaly where we had no anomaly previously. And in phase 6, we get a big change over the Arctic. But also, if we look over Europe, we have a kind of strengthening of this negative stream function anomaly, which was present in the first time period, so in the purple contours, but it's now much stronger in these green contours. So why does all this matter? Why are we interested in what's happening in the upper atmosphere? Well, it turns out that these will have an impact on our weather, and so I'm just going to show you how that will actually affect what we experience. So this is change in temperature. So it's the same as similar to the previous plots, but we're looking at temperature. Here, I've shaded the whole area difference just so that it's a bit clearer, and I've only showed the second time period contour just because otherwise it gets a bit messy. But the important thing is that we get a big change in the temperature response to the MJO. Over northern Canada, we have this massive cold anomaly in phase 1. If we look at phase 2, we don't see quite as much difference, but we do see warming over Europe, which we didn't see before, and cooling in California, which wasn't present in the first time period. In phase 5, we again get this big change over Canada. We can see actually pretty much following the Rockies, we have this kind of warming after MJO phase 5, which again is present in the second time period, but wasn't in the first. And then the real kind of headline for me is this big cold anomaly that we see after phase 6 in Europe. So this big cold anomaly wasn't present in the first time period, but is in the second. So what does this actually mean when we go back, kind of take a step back? Well, as I said at the beginning, the MJO can act as a source of predictability, so we can say something about what the weather is going to be like in America and Europe based on what the MJO is doing. But what we've shown here is that what we expect the weather to do in Europe is completely different depending on whether you look at the first time period or the second time period. So what we predict will happen after the MJO is changing on these kind of timescales. So I'll go back to these the original questions that we asked and kind of review where we're at. So do MJO teleconnections change on decadal timescales? We've shown that yes, they do. We have clear evidence that there are considerable changes in these teleconnection patterns, both in the upper troposphere and at lower levels. So in terms of the actual weather wheel experience. Are MJO teleconnections modulated by low frequency modes of variability? It's possible. We can't say for sure because unfortunately we just don't have enough data yet. We'd need to be measuring these things for many more decades to be able to properly answer this with observational data. But there is certainly a suggestion that these modes are involved. So that's something that we want to keep digging into a little bit further. Question 3, can we find evidence in the reanalysis data? Again, we absolutely can, and that's what we've shown today. And then question 4 is our kind of next step. Can we use climate models to provide greater insight? So the plan over the next couple of months is to use the CMIP6 coupled climate models to basically be able to increase our data set and be able to look at a longer time period. One of the great things about these CMIP6 models is that they have run these pre-industrial control runs where they effectively set the model going at pre-industrial forcing and just let it run for 1,000 years or so, which when we're looking at this kind of low frequency variability is great because we then have plenty of data to look at. We'd also like to have a look at the future climate change scenarios to estimate the effects of climate change on these teleconnections, but that's something to think about in the future. Okay, so that's me. I hope you enjoyed that talk. I just want to say a big thank you to my supervisors, Adrian and Dave, who helped me with this work. I wouldn't have been able to do it without them. If you'd like to find out a little bit more about what I've talked about today, of course, this was a very kind of quick overview. We are in the process of putting this together into a paper, so keep an eye out because that will hopefully be coming soon. And I'd love to chat to anyone about this work. Of course, you're welcome to ask questions once Ned has given his talk. But if you have any other questions, you can reach me on Twitter or at my website. Okay, thank you very much.
Great, great. Thank you, Dan. That was quite an insight and very interesting. Could I just remind everyone, please, there is a question answer box at the bottom of your screen. Please feel free to put any questions in, which we will ask both Dan and Ned after Ned has given his talk. And moving on, Ned, if you would kindly put your screen on, please. Your camera.
Hi, yeah.
Hi. Right, for your talk, we're moving a wee bit further north, and I think everyone can see there's a great deal of overlap between both talks tonight, which is really good, makes for a very interesting discussion. And just would like to introduce Mr. Ned Williams, Ned, from the University of Exeter, who is going to speak to us tonight on far-flung influences on the predictability of the North Atlantic winter climate. So, Ned, over to you. Thank you.
Thank you. Yeah. Can we all see that okay?
Yeah, can see it fine. Thank you, Ned. Thanks.
Brilliant. Thank you. Okay, so I'll get started. So as Gary said, this talk is on far-flung influences on predictability of the North Atlantic winter climate. And so I'll get started. To start off, I will introduce myself. I'm in the third year of my PhD at the University of Exeter, and I'm working with Adam Scaife, who's at the Met Office and the university, and James Green, who's a professor at the university. And my research focuses on seasonal climate prediction and interactions between the tropics and extratropics in the climate system, which are two subjects which are very closely linked. And prior to my PhD, I studied physics at the University of Southampton. And to briefly explain how this talk is going to go, I'll start off by introducing some of the key concepts to my field, including the El Niño Southern Oscillation and how it impacts global climate, and the concept of seasonal forecasting for winters in the UK and Europe. And then I will go on to a bit of my own recently published work with my supervisors called Underpredicted ENSO Teleconnections in Seasonal Forecasts. And if you don't understand what that title means, that's fine, because the aim of the first part of the talk is to hopefully make that clearer. So to start off with, I'll introduce the El Niño Southern Oscillation, or ENSO to its friends, which involves the fluctuation of sea surface temperatures in the eastern and central Pacific, with a warm phase known as El Niño. So on the right here, we've got the sea surface temperatures during a very strong El Niño event in the 1980s, where you've got these strong above average sea surface temperatures in the central and eastern tropical Pacific, and you've got colder than average temperatures in the western Pacific. And there's also the cooler La Niña phase, where you've got cooler temperatures in the central and eastern Pacific and warmer temperatures in the western Pacific. And as well as El Niño and La Niña, most studies define a neutral phase, usually when the temperature change over a particular region around here in the Pacific is less than half a degree from average. And an important thing about ENSO is that it varies relatively slowly to the, compared to the weather. So, for example, an El Niño or La Niña event usually lasts months, if not years, mainly because it's an ocean process and the ocean tends to vary more slowly. And although they're the first order pretty opposite, they're not quite mirror images, with El Niño events usually being stronger and extending further to the east than La Niña events. We can see that in these figures, with the El Niño event here having a big impact on the coast of South America, whereas the La Niña event barely touches the coast. And also La Niña typically lasts longer. Just this month, actually, a 3-year La Niña event just ended. And it's very rare to have a 3-year La Niña event, but it's unprecedented for an El Niño event to last that long. So although it's rare for La Niña, it would be even more unusual for El Niño. And I'll just briefly go over how ENSO was discovered, because I think it's interesting and it adds to the picture. We know that ENSO-like variability has existed since at least the Ice Age, and we know that because of paleoclimate records, such as coral reefs here. Essentially, when you've got warmer ocean temperatures, corals get bleached, which is very sad and is happening more because of climate change. But it does mean we've got records of the historical climate. So it does tell us a bit about the world. So that's nice. And in the 19th century, fishermen in Peru noticed that during winter, there would be warm currents along the coast, and these would bring fish in December. And so they named it El Nino, which means the male child in Spanish, in a reference to Jesus, because they thought this is a good thing that happens in December. And something that the fishermen and later scientists noticed was that on some years it was extremely warm, and that became the scientific concept of El Nino. And the reason they discovered El Nino and not La Nina is because, again, back on the previous slide, El Nino tends to reach the South American coast, especially during strong El Nino events, whereas La Nina usually doesn't. And then it was later on in 1924, Gilbert Walker, English scientist, looked at long-term weather time series data across the world, and he noticed that pressure in Darwin in Australia here correlated well with pressure in Tahiti here, or was anti-correlated. So when one was high pressure and one was low pressure. And I've attempted to show the correlation between the difference in pressure between the two and the pressure at a particular point in this map. So he found this big large-scale climate link, but he didn't know what was causing it. And it was in 1969 that a scientist called Jacob Bjerknes realized that El Nino, which at the time was still considered a phenomenon that happened at the coast of Peru, was heavily linked to the Southern Oscillation. The two are correlated. And then later on in the 1970s and 80s, measurements of the Pacific Ocean away from the coast, because we didn't originally have many observations away from the coast, because that's where people lived, they became better, and it became clearer that El Nino is something that happened across the whole ocean. And also its opposite counterpart, La Nina, became more evident and finally got a name. So that's basically a history and an explanation of what the El Nino Southern Oscillation is. The mechanism behind ENSO are very, very complex, and there's a lot to it, but I'll try and go through the very basics. During neutral conditions, so when there isn't an El Nino or La Nina, the West Pacific is actually warmer than the East Pacific, and it has a deeper thermocline than the East Pacific. And what we mean by the thermocline is that it's the part of the ocean where the warm upper ocean temperatures rapidly become the cold lower ocean temperatures. So it's a big, sharp vertical pressure gradient. And so what can happen is that a small warm anomaly in the East Pacific, perhaps just caused by weather events, will lead to trade winds, which go further east. And that's because of changes in pressure due to the changes in temperature. And this leads to a positive feedback loop, because the warmer surface ocean in the West Pacific moves further east, and it gets warmer and warmer in the East Pacific until we get a fully fledged El Nino event. But eventually El Nino limits itself, for example, by the thermocline depth, because the difference in the thermocline becomes much smaller during El Nino, but it can only get so deep in the East Pacific. And once it limits itself, it starts to decay gradually, falling back to neutral conditions, but very often overshooting into La Nina conditions, and the East Pacific becomes cooler than average, the West Pacific becomes warmer than average. And on a similar vein, La Nina can grow out of small cold anomalies in the East Pacific, and then when it starts to decay, eventually overshoot to El Nino, although this is actually definitely less common than the other way around. So we know the mechanisms behind ENSO. Since the 60s, 70s, and 80s, we've had fairly good ocean observations. This gives an opportunity to forecast ENSO. Unfortunately, in the early years, ENSO forecasting faced several issues. Satellite observations started to become a thing, particularly in the late 1980s globally. The early 1980s. And in 1982, a strong El Nino event started to happen. But unfortunately, a volcano called El Chicon started erupting in Mexico at around the same time, which led to loads of ash obscuring the satellites. And so they didn't realize until the El Nino event had already started that the temperatures were getting warmer and warmer in the Pacific. So early attempts to forecast ENSO weren't so successful. Nowadays, forecasts for ENSO are made using complex coupled atmosphere-ocean climate models, like we use for long-term climate projection. And luckily, although it needs a lot of computing power, that is very much worth doing, because ENSO is well forecast up to around 9 months ahead. It does partly depend on the time of year you're starting the forecast, and they can be very inaccurate at 9 months ahead, but 3 to 4 months ahead, they're pretty much solidly accurate, and there's a good amount of skill 9 months ahead as well. So here is, we've got a smoke plume here, we've got what's called a forecast plume here, which basically shows all of the possibilities according to the model of what could happen. And as you can see, we're currently in below average ENSO conditions at the moment, but we're likely to progress into an El Nino event come this summer. So I've gone on a lot now about the tropical Pacific phenomenon called ENSO, but what stays in the Pacific doesn't, what happens in the Pacific doesn't necessarily stay in the Pacific. And in fact, the El Nino Southern Oscillation has a global impact on year-to-year climate variability. And if you read a paper on the El Nino Southern Oscillation, about half of them have a sentence at the start, which is pretty much identical to this one, including a paper of my own. And these remote impacts of the El Nino Southern Oscillation are known as teleconnections, and closer to the source, so closer to the tropical Pacific, they're more robust the teleconnection. And basically what we mean by that is that each time we have an El Nino event, for example, in South America, you'll get hotter temperatures, whereas further away, there's more variation in what El Nino can do, because there are more ways that the teleconnection can travel, and also other factors such as the MGO that Dan was talking can have a big impact. And as well, the nature of the teleconnection depends on the seasonal cycle. For example, here in Japan, the temperature is warm during an El Nino event one part of the year, but cold in a different part of the year. And partly because La Nina isn't just a pure mirror image of El Nino, the teleconnections themselves aren't always a mirror image. So in particular for this talk, we're interested in the impact of the El Nino Southern Oscillation on the North Atlantic. And I would say the main teleconnection, somewhat similarly to what Dan was showing, actually travels via the North Pacific and North Atlantic. And this part of the teleconnection has been well established and is quite robust. And basically what you get during an El Nino event is you get high pressure over Hawaii, lower pressure over the North Pacific towards Alaska, higher pressure over Canada, and lower pressure going into the Southeast United States and into the Atlantic. And this is pretty solid. This happens in pretty much any El Nino event, and La Nina teleconnection is basically the opposite to this. But it can also extend further into the east, leading to pressure anomalies in the North Atlantic. Although this is known to switch sign between the early and late winter, as I try to demonstrate here. Actually, this is from a paper that already exists, but as this figure demonstrates. So during El Nino, during November and December, you usually get a low pressure anomaly over Iceland and Greenland, whereas in the late winter, you get a high pressure anomaly over Greenland and Iceland, and you get a low pressure anomaly further south in the North Atlantic. And you get broadly the opposite during La Nina. And this is important because these pressure changes lead to a change in something called the North Atlantic Oscillation, which is fluctuation of pressure between where there's usually low pressure around Iceland and high pressure west of Spain around the Azores. So during El Nino in late winter, the teleconnection maps quite well onto this North Atlantic Oscillation, but it's opposite in sign. So this is a negative NAO response. And during La Nina, you get a positive NAO response. And the reason why we're interested is because this north to south pressure gradient is very, very closely linked to the strength of the jet stream. So when we've got a positive NAO, we get more winds because that's what the jet stream is, but also the jet stream comes up from the Caribbean up to Northern Europe. So we also get higher temperatures brought up, but also more storms, so more rainfall. So during La Nina, when we've got a positive North Atlantic Oscillation on average, we're likely to have warmer, wetter and windier conditions in late winter. And the opposite is true during El Nino. And finally, for this slide, the teleconnection also travels via the stratosphere, which is part of the reason for this shift between early and late winter, actually, but not the only reason. And also during strong El Nino events, it can travel via the tropical Atlantic. So this is quite a complex process, which can have a lot of variation. So we know how El Nino and La Nina affect the North Atlantic Oscillation. We know that the North Atlantic Oscillation is important for UK and European climate, and we also know about several other factors that can affect the NEO, including the MJO that Dan was talking about earlier. And this means we can do seasonal forecasts for European winters. And what a seasonal forecast is for winter is it will be initialized in November, and then we'll try to predict the climate for December, January, February, and often into March. And this is important because if it's colder than usual, for example, energy bills might be higher. If we've got less wind, there'll be less wind power, and there are various applications. So the seasonal forecast we have used models similar to those used for long-term climate projection, also similar to weather forecast, but actually, although the timescale is more similar to weather, the models are more similar to the longer-term models. And we use an ensemble method, which basically considers errors in the initial conditions of the model, but also uncertainty on what can happen in between when we start the forecast and when we forecast to, basically to take into account all of the possible trajectories of the climate system, which on here, these are what the little dots show. And what we find is after we run these complex models many, many times, we get skillful forecasts, so they are useful. This black line is the observed NEO, this red line is the forecast NEO. Although it's weaker, the red line is usually positive when the black line is positive and negative when the black line is negative. But yeah, this predictable variability, which is what's kind of in the mean, the red line here, is known to be underestimated, unfortunately, in forecasts of the NEO. And this has become known as the signal to noise paradox, which is a bit of a problem because it means forecasts are less accurate. It means you need more ensemble members. So we want to go about solving it. So yeah, that's basically the background to my research. And now I would like to show a bit of research that I've recently had published and is broadly the first half of my PhD. So in this work, I focus on January to March because that's when the teleconnection is strongest, not only in the North Atlantic, but also in the North Pacific. I look at forecasts from 5 centres, the Met Office, the Europe-wide ESMWF, the Italian CMDC, the German Deutsche Wetterdienst, and Météo France, and there's no prize for guessing which country that. And I use hindcasts, which is similar to a forecast, but instead of starting from the current conditions and looking ahead, it starts from past conditions and predicts what's already happened in the past. And the advantage of that is we can compare these model runs to observations and see how well the forecasts, or rather hindcasts, work. And for this work, we split years into El Nino, La Nina, and neutral. We're showing the El Nino teleconnection. This is geopotential height, which is basically equivalent to pressure. I'm looking in the middle of the troposphere because that's where the teleconnections kind of travel. And in the extratropical regions away from the tropics, the teleconnection is pretty similar, whether you're at the surface or you're right at the top of the troposphere. And if we compare the observation on the left to the multi-model mean on the right, it's pretty accurate. You get this rising all throughout the tropics. You get a strong negative response in the North Pacific. You get a strong positive response over Canada, and below that you get a negative response with both of these extending just into the North Atlantic. If you look at the observations and the multi-model mean, the results are very similar. However, as you probably noticed, particularly in the North Pacific, the strength of the connection is much, much weaker than observed in the multi-model mean, which is not what we want. This is clearly a problem. It means that we don't properly capture how El Nino and La Nina affect North Atlantic climate. And this is true in all 5 of the models below here. So we found this problem and we wanted to expand on it. We focused on the North Pacific because that's where the teleconnection is very strong and robust. And we looked at El Nino and La Nina and multiple different levels in the troposphere. So from approximately surface all the way to the top of the troposphere where the stratosphere starts. And as we can see, all of the models are weak during El Nino. This black line is observations, and the coloured lines are each of the models. Most of the models agree with each other, with the Météo-France model being a bit weaker. So this is a problem throughout the troposphere and for all models. When we look at La Nina, we get similar results. Some of the models aren't that weak, and there's a lot of spread between the models, but all of the models are weak and throughout all of the troposphere, really, maybe not at the very top. So this is clearly a widespread problem. We want to be able to fix it. To fix it, we need to know what causes it. So what I did was I looked at precursors of the teleconnection, starting with the sea surface temperatures themselves, because if during an El Nino event the East Pacific doesn't actually get that warm, that would obviously cause a weaker teleconnection. However, when we looked at it, that wasn't the case. So these black lines here show 3 different observational data sets with error bars on, basically showing whether results are significant or not. And these 5 coloured bits are the individual models, with the orange line being the multi-model mean. As you can see, the models tend to agree with each other quite well, and the orange line is above the mean of all of the observational data sets. It's well within error of these 2, although this 3rd data set is quite a bit lower. That's probably because it uses a different set of years. So what we see from this is that the sea surface temperatures changes during El Nino aren't underestimated. If anything, they're overestimated. So the next step we looked at is tropical rainfall. This is obviously very important for tropical regions themselves, but also they are essentially how the sea surface temperatures affect the extratropics. The teleconnection wouldn't exist without the rainfall changes. And so I started off looking at the East Pacific, where you get wetter, more rainfall during El Nino, and that's because warmer temperatures in the tropics lead to more rainfall through convection. And there's a bit of spread between the models, but they're all within error of the observational data sets, which strongly agree with each other. The multi-model mean is about 95% of observed and well within error, so that's not too weak. In the West Pacific, where it gets drier, this is around the Philippines, maybe a bit further to the east. The models agree with each other quite well, and this orange multi-model mean line sits between the means of the 3 observational data sets, even though there's not much disagreement between those data sets. So that's definitely not weak either. So what we found here is that the tropical rainfall response to El Nino isn't weak. We did look at Rossby wave sources and got very similar results. So if anyone's interested in that, I can go through that a little bit later. And yeah, despite the tropical forcing of the teleconnection being pretty accurate in the models, the teleconnection really is weak. So we looked at this North Pacific response again to El Nino. Again, the orange line is the multi-model mean, and this is below the 95% confidence interval for the 2 observational data sets, and it's about half of that observed. So this is a real problem. It's not just statistical noise or anything like that. And the story is pretty similar in all 5 of the individual models. So what we've gathered is that the El Nino teleconnection is weak, yet the forcing of it that comes from the tropics isn't weak. So the problem seems to originate in the extratropics. And there's something called eddy feedback, which is quite likely to be the cause of this, I think, but we haven't actually looked into this. So that's not yet proved to be the case. And this is for El Nino. The La Nina teleconnection also is significantly weak, but also the tropical rainfall anomalies were found to be weak, which suggests that the La Nina teleconnection issue could partly come from the tropics as well as the extratropics. We weren't as sure on that. So we found out that the teleconnection between El Nino and La Nina and the North Pacific is weak. We've partly established why that is, but we were originally interested in the North Atlantic in Europe. So we looked at the teleconnection from the North Pacific to the North Atlantic, essentially because this tropospheric teleconnection is much more robust and much more simple than the full El Nino and La Nina to North Atlantic teleconnection. And basically we looked at where the pressure was lower or higher than average in the Pacific Ocean, the North Pacific Ocean, and then saw how the North Atlantic responded to that in observations on the left and the multi-model mean on the right. And if we look at the sort of North Atlantic Oscillation region here, you get a positive pressure anomaly around Iceland and a negative pressure anomaly west of Spain. This is true in the observations and the model, although perhaps the anomalies extend a little bit too far in the model. And the strength is pretty accurate in the models as well. If anything, it's a little bit too strong, but in the core NEO region, I think the strength is pretty accurate. So what this tells us is that if we got the North Pacific teleconnection right from ENSO, the North Atlantic teleconnection will be much more accurate. And this is important because El Nino and La Nina are very predictable. So if the teleconnections coming from them are very accurate, we have a predictable component of the variability. And this is clearly weak because of this problem in the North Atlantic. And so this problem is clearly somewhat related to the signal-to-noise paradox, which remains unresolved. So hopefully this tells us a bit about it. And so to summarize that, teleconnections from El Nino and La Nina to the North Pacific are underestimated in seasonal forecasts. This is a problem that exists throughout the depth of the troposphere. During El Nino, the problem largely originates from the extratropics. We're a little bit less certain about La Nina. And the weak teleconnection to the North Pacific leads to a reduction in the predictable variability in the North Atlantic, which relates to fairly well-known errors in seasonal forecasts. So yeah, that's all I had to say. Thank you very much for watching. Any questions would be greatly appreciated. You can also contact me on my email, and please do follow me on Twitter if you're interested. And also I've got a link to my paper here, which is open access, so anyone can read it. Thank you very much.
Well, thank you very much, Ned. That was absolutely fascinating as well. And obviously, a considerable overlap in data between yourself and Dan. So it's really interesting to see the models that you've both been using and how it's interesting to see how they would actually compare. Okay, thanks again. And some questions. Could I ask if anyone has any questions to ask? Please put them on the chat at the bottom or the question page. We have one question from Len. In the first instance, it was actually, Len, it was actually, I think, originally addressed this one to you, Dan, but I think it's very much appropriate to both of you, actually. In the first instance, the atmosphere drives the ocean circulation, and this affects sea surface temperature. So, are you concerned with feedbacks? It is all rather non-linear. Dan, do you want to go first?
Yeah, absolutely. Thanks, Len, for the question. It's a really great question. So yes, absolutely. There are feedbacks between the atmosphere and ocean, and so this is something to consider. In this particular piece of research, it's not something that we're thinking about directly. We're looking more at changes in the average sense. If you were looking at particular events, then yes, you'd probably need to look at this a little bit more. But I think the key thing here is the timescales that we're looking at. So the MJO works on a kind of 1 to 2 month kind of timescale, but what we're looking at is how these connections change on decade to decade timescales, which is much more the kind of ocean domain. So yes, there will be feedbacks, but because the feedbacks work on different timescales, it's not something that we're looking at directly. We're kind of taking it as part and parcel of the of kind of decadal variability in a sense.
Okay, thanks, Dan. Ned, do you want to add anything to that?
Yeah, of course. Yeah, so yeah, it does have relevance to what my bit, I guess, as well. So yeah, I guess with the origin of El Nino and La Nina, it does require these surface winds really. So it is a coupled atmosphere-ocean process. Where it comes to my bit of work with teleconnections, there is a little bit of a link between the atmospheric circulation on the troposphere onto the tropical ocean. I think that's more of the case on decadal timescales rather than seasonal timescales, but it is a thing and is worth studying. I think it's not too important for the results I found because the weak teleconnection is unlikely to lead to accurate tropical conditions, if that makes sense. So luckily, the way it's happened, where we've got good tropical conditions and poor extratropical conditions, kind of does prove which way around it's happening, which is good to know. And also, I guess on a seasonal timescale, I think that ocean temperatures are much more still, whereas the what happens in the atmosphere is a bit more chaotic.
Thank you. There's another question. It's from Gregory Wolverson. Greg, he asks, does the ENSO predictability vary depending on the phase, and where in the phase are we? For example, does the predictability lower in the transition phase we are currently experiencing from El Niño and El Nino?
Yes, yeah. Great question. Yes, it does. In the first instance, if you have an El Nino event, it's pretty likely to eventually transition into a La Nina event. If you've got a La Nina event, you can't say too much about what's going to happen next. It's not as likely to overshoot into an El Nino event, although it does happen. If you've got neutral conditions, it's a little bit more likely, I think, to spring into an El Nino event than a La Nina event. But on its own, you can't say too much. As about now, we're just exiting La Nina, and it does look, the forecasts do look like an El Nino event is likely to happen. Unfortunately, at the moment, this is the worst time of the year for the forecast. They're the least accurate at this time of year. But the forecasts do seem to be converging on it a little bit. So that does say that it's quite likely. Another thing is that forecasts do have a bit of a persistence bias, I think, in which if you've got current warm conditions, it over-predicts the chance of an El Nino happening. If you've got current cold conditions, it over-predicts the chance of a La Nina happening. But yeah, I guess, yeah, so I think that's all I can say. But I suspect the forecasts are more accurate coming out of an El Nino than coming out of a La Nina, which is a bit unfortunate at the moment, but yeah.
Okay, thanks, Ed. Dan, do you want to add anything to that one?
Yeah, I mean, being ENSO, this is very much more Ned's domain than mine. So I kind of echo what Ned said. I mean, one thing that does have an impact on the predictability of ENSO is the MJO, the Madden-Julian Oscillation, which I talked about. Of course, these things do happen on slightly different timescales. So the MJO happens slightly faster than ENSO. But if the timings are right, then the MJO can modulate changes in ENSO. So depending on, I mean, of course, if you look at the kind of spatial domain, where you've got that kind of increased convection moving into the West Pacific, that is going to then overlap with that kind of warm or cold tongue from the tropical Pacific from ENSO. And so you can actually, if the MJO kind of comes along as ENSO is kind of transitioning, it can kind of give it a bit of a kick in a sense. So that is another factor when thinking about ENSO predictability.
Okay, thank you, gentlemen. Just I'd like to pick up on something that you mentioned in your talk, Dan, and it's appropriate to Ned as well. When when you were looking at the models, and particularly Ned, you had used 5 models, and they were surprisingly close together, the results. And Dan, you referred to reanalysis of these when you were talking in yours, but did you find any significant variations during the reanalysis that would be of concern?
So in the reanalysis, not so much. Certainly over these kind of timescales and on large kind of spatial scales, reanalysis and observations pretty much become interchangeable. The reanalysis models are really, really good at getting the large scale things right. If you look at kind of much smaller scales, so you're looking kind of kilometer kind of scales, and you're looking at particularly things like ocean atmosphere feedbacks, that's where the reanalysis can get a little bit more sketchy. But on these time and spatial scales, the reanalysis is pretty solid. One, as I said, the next step for me is to look at kind of coupled climate models. When you look at those, you do start to see more issues. I mean, at the end of the day, they're predicting things on a much greater time scale. They're looking at things. It's not so kind of close in a sense, so it's harder to predict kind of further forward. But Ned can probably say a little bit more about that because he's kind of been looking at the models in his work.
Thanks, Dan. Ned?
Yeah, sure. Yeah, so one thing I would say about reanalyses is that some things are have inaccuracies. So things like pressure and geopotential height are pretty accurate, but I do know rainfall. Reanalyses are pretty accurate in where there is rainfall, but not always accurate in how much rainfall there will be. And that's something, rainfall, that models are quite bad at, especially the long-running climate projection models. So that is a problem. As for the seasonal forecast I looked at and where they differ, definitely in the case of La Nina, when I looked at that, there was a much more variation in the rainfall and what I called Rossby wave sources. There seemed to be a lot more disagreement in between the models. And I think this is kind of a problem because it means you have to understand what's causing the issues in each individual model. There may be multiple different issues where some models are worse, some models are better, and it's kind of, you may try to make models better and accidentally make them worse. So that is difficult. It is nice in a way when models are all wrong in the same way, although it does mean they're all wrong, whereas if they vary a bit, some models might be better than others, which is useful.
Okay, thank you. Just one other question. It's a slightly tongue-in-cheek with this one, Ned, but you made a reference in your talk, quote, to fix it, we need to know what caused it. How confident are you that there is a problem because of climate change? Well, we will all accept there is a problem, but how bad is it? And are you, how do you think that we will find what the problem causes it, what the causes are, and will we find a fix for it?
Sorry, do you mean for the cyclic noise paradox? Or?
Yeah, sorry, yes.
Yeah, of course, yeah, that's fine. Yeah, so there has been a lot of research on this, not just by myself and by lots of different groups, often taking very different approaches, but I think complementing each other very much. And I think this problem was kind of first discovered in the early 2010s, so it's been around for about 10 years. I think there's a lot more agreement and it's a lot clearer sort of what's going on now than it was then. And I do think, like, back then, no one was really sure. It was more of a statistical issue. Nowadays, I think most people would agree it's a fact that causes of predictable variability are weak. And perhaps increased resolution models, which can, especially if it's eddy feedback is the issue, will be the solution. Perhaps it'll be something else to sort of get rid of the problems that are involved with the seasonal, with the cyclic noise paradox. You can use a larger ensemble because the larger the ensemble, the more you can extract a signal from the noise. And that means you can be more confident whether you're more likely to have a negative or positive NEA or whatever you're trying to predict. It's not just the NEA, there are a few other things affected by this. You do still have the problem that the ensemble mean is too weak, and there's a little bit more uncertainty than you would have of the effect of this predictable variability. But to some extent, you can scale that up to what's happened in the past. So you can kind of get around it without fully solving it, but I think we'd be much better off if it can be solved. And I'm fairly confident that it will eventually be solved.
Good, thank you. Well, no more questions. So both of you, thank you very much. On behalf of the Scottish Centre, I do thank you, and we wish you the best with your studies going forward, and look forward to reading your published results. They both sound fascinating subjects, and the crossover is quite remarkable, actually. Very similar, but approaching it from different points of view. So it's a very interesting talk. So thank you very much. And to the members of the public that are still with us, I would thank you for attending tonight, and we hope to see you at future meetings. And just before you go, I would like to thank, there are, an exercise like this, and does take a bit of behind the scenes work. So we've got three other people behind the scenes working on this to make sure it all runs smoothly and you stay connected. There's Hayley from RMetS head office in Reading, so thank you, Hayley. There's Richard and Alan from the Scottish Centre, who are always on hand to make sure things are just perfect, and if anything goes wrong, they step in or fix it. We also have tonight, as part of our team, Greg Moverston. Greg is taking over from me as the president, vice president for Scotland and the chairman of the Scottish Centre. So it was nice to get your question, Greg, and we are going to look forward to you being up front in the chair here in the future. So thank you very much, everyone, and we look forward to seeing you at our next talk. Please always check in on the RMetS website. All the information's there, and all the dates, forthcoming meetings, not only for the Scottish Centre, but the RMetS do an awful lot of talks that are very interesting, great speakers and great subjects. So please keep an eye on the talks that are coming up and join in if you can. So thank you very much again for joining, and hope to see you at our next talk. Thank you.